Ciao, Internet. This is your captain speaking, Lester Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary. This is From First Principles. My friend.
How's it going?
We have some travel coming up, and so we want to do a quick special episode for this upcoming week, which just so happens to be when the World Series is happening.
Mm-hmm.
And so, as you can see, we've prepared accordingly with our Japanese Ohtani jersey, with our Dodgers memorabilia, hat, because we know the Dodgers are going to be back-to-back World Series champions.
That's right. I mean, we're recording this a week before the World Series, but we already know how it's going to go down.
We already know how it's going to go.
Yeah, it's going to go down. I mean, we're going up against Canadians.
Look, having been on both sides of the pond, born in Montreal.
You
living in the States.
Yeah, you're literally kind of Canadian, but you know what I mean.
It's not the same thing. It's not the same thing. We are going to win, but because of our sort of travel schedule, we're going to do a special episode that's focused on one story, and this story actually comes from a direct message, a DM. Mm-hmm. Someone slid into the DMs on TikTok, and they mentioned the recent passing of a physicist named Chen Ning Yang.
Yep.
And people are saying he's one of the most influential physicists of the 20th century. And I was unfamiliar with the game, did a little bit of digging, and some of the names that people associate in terms of the class he belongs in include Einstein, Bohr, Heisenberg, Feynman. High praise.
Yeah.
Very, very high praise.
Yeah.
So are we really saying that Yang can be associated in that class of sort of untouchables when it comes to sort of physicists who are above reproach in terms of what they've provided over the course of their careers in knowledge and expertise in Nobels?
He won the Nobel Prize, and everybody talks about that, right? There's a BBC article that came out on his death, and it said, Chinese Nobel laureate and physicist Chen Ning Yang dies at the age of 103. That BBC article mostly talks about his Nobel Prize, which was given for discovering the theoretical foundations for something called Parity Violation, which is what we're going to get to. But that's not actually why he's considered one of the greatest of the 20th century. I mean, as you said, the 20th century has some of the most influential physicists of all time. Einstein, Bohr, Heisenberg. These are the people who not only contributed to our understanding of the modern world, but totally reshaped how we think about doing physics in the first place, right? Mm-hmm. And Yang is one of those people who completely kind of changed the way in which we think about trying to do theoretical physics, as theoretical physicists do. And he came up with the thing that really immortalized him was his formulation of something called non-abelian gauge theory, which is known as Yang-Mills theory.
I remember hearing, gauge theory all the time.
This is the guy who kind of started that whole thing, okay? Yang-Mills theory, and in physics circles, we just say Yang-Mills theory. It's a bedrock foundation for the Standard Model, which is one of the most successful theoretical ideas that we've had as human beings, okay? And it's rooted in this idea of symmetry, okay? So in this episode, what I really want to do is go through some of Yang's work and talk about symmetry as a principle and how that relates to the modern world. Now, symmetry, everybody knows what symmetry is, right? My favorite symmetric object is the Taj Mahal in India. The first time I saw it was actually I was quite old, even though I grew up and was born in India. I didn't see it until after college, and it is one of the most beautiful buildings I have ever seen on planet Earth. And all of that has to do with symmetry. If you look at the Taj Mahal, right, it's an extremely symmetric building. And we kind of know what that means, right? We have this deep sort of intuitive sense that symmetry means balance, beauty, harmony, right? But when we think of symmetry, we think of it as a static property. It's something that we're looking at for a static object, right? But what do we actually mean when we say symmetry? The idea is, and this is something that the great mathematician Hermann Weyl came up with. The idea of symmetry from a mathematical sense is that a thing is symmetrical if there is something we can do to it so that after we have done it, it looks the same as it did before.
This is a tongue twister.
It is. But here's what's happening. You've got a thing that is symmetric. Okay. What does that mean? That means I can do something to it, and when I'm done doing it, it looks just the same. The Taj Mahal, here's an example, right? Imagine the Taj Mahal in your head.
Yes.
Flip it. Flip it along the XY plane.
Yes.
No, not on the XY plane, on the vertical, right?
Yes.
So everything that's on the left goes to the right. So those spires on the left go to the spires on the right. The dome is exactly symmetric to the central axis. The two little domes on the side are symmetric, so they just flip around. So you can imagine if I were to take that photo of the Taj Mahal and then flip it right along the middle, I would get the same exact Taj Mahal. That means that it's symmetric.
Okay.
Does that mean?
Yes.
Does that make sense?
Yes.
It's symmetric upon reflection of that central axis.
Yes.
Now, there's other kinds of symmetry, and we're used to it. Like, for example, there's shapes that we can do, and what we can do is not just reflecting along the central line, we can reflect along many lines. For example, the heart shape, you can reflect along the central line. The butterfly, you can reflect along the central line, and the wings will go from one to the other. A square, you can reflect along the central line on both axes and also along the diagonals, and the square is going to come back to be the same square. Okay? There's another way to do symmetry, not just with the reflections. You can also do rotations of objects. If you look at like the red cross, the cross of the red cross, or the thing that's in the middle of the Swiss flag, right? You can rotate that cross 90 degrees, and it'll be the same cross, right? But if you take an arrow and you rotate it, it's going to point the other direction, right? It's going to point from up to left or whatever, however you do the 90-degree rotation. So in that sense, we kind of know what symmetry means for objects, like thingies, right? 2D things, 3D things, you can even think about a sphere, right? You can rotate a sphere in any direction, and it's a continuous symmetry because no matter how you rotate the sphere, it's still going to be a sphere.
And you can do similarly with a cube, but only not in any direction, but in certain explicit degrees of rotation.
Yeah, and actually the 5 platonic solids that are our logo, you can rotate them in 3 dimensions, and you'll come back with the same exact platonic solid.
Yes.
Right? So we're used to objects being symmetric, but in the early 1900s, there was talk about maybe there's symmetry in the physical laws themselves. Okay? There's stuff you can do to physics laws that leave the physics laws exactly the same.
Okay. I hear what you're saying.
Yeah. So let's dig into that. This was actually first sort of codified by someone by the name of Emmy Noether, who was a mathematician from Göttingen. She was actually people didn't want to publish her because she was a woman, so she would publish under her supervisor's name. But there's a theorem called Noether's theorem, which basically codifies this idea that there's something I can do to physical laws that will preserve the action of the physics underlying it. There's we've actually it's quite intuitive at the start. Okay. There's a translation in space. That's a symmetry. For example, the laws of physics are the same here as they are anywhere else in the universe.
We've talked about this.
So and we've talked about this before. If I set up an experiment here in one lab, and I do some thingy and I measure some thingy, and then I go all the way across the United States to the East Coast, and I set up the experiment, I'm going to measure that same thingy, right?
LIGO is a perfect example of this.
Yes, exactly. There's one on Livingston, there's in Louisiana, and there's one in Hanford in Washington. They're both operating the same way. This LIGO wouldn't be possible if translation in space wasn't a thing. Right?
Yes.
Right? But there's an inherent assumption there that because we're on 2 separate parts of Earth, the Earth is not really part of the experiment. right? We're doing enough to cancel out the stuff of Earth and like that local environment to really focus on the physics that we want. And because of the translation symmetry of physics, that experiment in Louisiana is the same as the experiment in Washington, right? That's a translation in space.
Okay.
There's also a translation in time, which means if I do an experiment now and then I don't change anything and then I do an experiment, tomorrow or a month later, as long as it doesn't somehow depend on the Earth's position in the solar system or something like that. Obviously, if you're trying to like measure stars or something, yeah, you're not gonna.
Sure.
Yeah, but if you're doing something with subatomic particles or like gravitational waves, then yeah, whatever thing I'm doing now is the same as what I'll be doing tomorrow, is the same as what I'll be doing in a month, and so on and so forth.
Is this the kind of where this idea of longitudinal studies come from, where you have this long period of time where you're just replicating the same experiment in order to see the impacts, like over generational differences or any other kind of category? But because you have this symmetry in time,
you at least can trust that the laws of physics aren't changing. Right?
That's not a variable.
If that weren't true, then it's like whatever thing you're doing, it's like, oh well, you did it a month later, right? So there is this like underlying notion that whatever the laws of physics are today are going to be the same as the laws of physics tomorrow and the day after, right? And another one is the rotation in space. Okay, if I have an apparatus that's oriented this way, and then I just rotate the whole thing, as long as like I rotate everything that has to do with my experiment should yield the same results, right?
Makes sense.
So all of these things are symmetries. The fact that I can change my experiment in a way, but the physics remains the same. This is underlying, like, the fact that I can replicate experiments. And if I do an experiment and I publish something with all the methods, somebody from the other side of the world can actually replicate that experiment.
It's the bedrock of the scientific process.
It is. And it's been shown to be true. There's so many experiments that show that, this is the laws of physics. There's no special point in space and time or direction in space and time that like yield different laws of physics, right? Emmy Noether, in Noether's theorem, what she actually showed was, if we take the assumption that physics is the same after these translations, then something must be conserved every single time that we have this symmetry. That's something that we can tackle in a later episode and actually prove Noether's theorem. It's a beautiful proof, and it's quite intuitive. But at the end of the day, what ends up happening is any symmetry is associated with a conservation law. So, for example, the fact that I can translate in space, meaning I do an experiment here, then I do an experiment somewhere else, and the physics laws are exactly the same, that leads to a conservation of momentum. Okay?
Yes.
In any situation.
Right.
If I do an experiment today, and then I do it tomorrow, and the week after, and the month after, and all of the laws of physics are the same, that leads to a conservation of energy. Okay? If I do an experiment here and I change the rotation, where I rotate my entire experimental apparatus and I do it again, and the laws of physics are the same, that leads to the conservation of angular momentum. Right? It's a deep, deep notion that we have. Okay, this was in the early 1900s where Emmy Noether came up with this.
I've never understood it intuitively because we've talked about all three of them. We've talked about conservation of angular momentum quite a bit. We've talked about the conservation of energy, and the conservation of momentum. And I've never understood it intuitively in this context of, if you're doing your experiment here today and there tomorrow, there is
no difference, which means and according to
that's actually very. I just had a light bulb go off in my head. Apologies.
It's so deep, dude, to think about, right? That like really like these laws that we have, these rules that these numbers are never going to change in any given setup, has to do with the fact that the universe wants to conserve the laws of physics regardless of these transformations. Right. It's a very deep statement to make.
Yes.
Okay, and that's something that Emmy Noether came up with Noether's theorem. Now, she did that for classical mechanics. This is before the quantum revolution and things like that. And Hermann Weyl was one of her colleagues at Göttingen. he thought this was one of the craziest things he's ever heard, right? The fact that you can connect like an action on the physical laws to a conservation of the physical laws themselves. And he started going further with the new quantum revolution and trying to put that into this same language. Okay. And turns out it gets even deeper when you go into quantum mechanics. In quantum mechanics, for example, everything is a wave function, right?
Yes.
Whatever that means. But what gets even weirder is that wave function is a complex number. Okay? It's a complex number, which means it has a magnitude and it has a phase. It has a phase with respect to like some kind of zero, some zero that you arbitrarily choose. That complex number it's like a clock hand, right? It's got a length and it's got an angle. Well, according to quantum mechanics, what are the observables? The observables are probabilities of outcomes of experiments. And that comes from taking the magnitude of this complex number, the magnitude meaning only the length. So the phase actually doesn't matter when it comes to things that we can see, right? Which means if I take an electron, for example, and I change the phase everywhere for that electron, all over the universe, right? Because this wave function is everywhere. That's not going to change the outcome of my experiment. If I add a phase or I subtract a phase, if everywhere I'm just like making the clock go a little bit, that's not going to change whatever thing I observe.
Right.
Okay. And it turns out that symmetry has to do with the conservation of charge. The fact that I can't create a positive or a negative charge anywhere. It's crazy, right? So this is getting real interesting.
Oh, interesting.
This is getting really, really interesting.
Okay, please continue.
Right?
Because it's again, from that foundation, I'm extrapolating to a variety of other things we've talked about before that are making even more sense understanding this like correlation or this relationship.
Yeah, physics is getting really weird and really beautiful at the same time, right? It's like, it's getting weird. In any case, let's talk about, okay, so we've talked about symmetries, right? And like the laws are going to be the same no matter what I do.
Yes.
Okay.
Both in a classical sense
and we've just touched upon the quantum sense of things, right? Okay. So let's talk about something that does break symmetry, because not every transformation is going to preserve the laws of physics. For example, if you do a change of scale, right? Suppose I make my experiment and it's like, 1 meter by 1 meter or whatever, and then I just like increase the size of my experiment. Am I going to get the same physics? The answer is no, because nature does have a fundamental scale, right? There are such things as atoms, and those atoms are about 10 to the minus 10 meters big, like 1 angstrom, right? So to make my thingy bigger, I need to use more atoms, and that's going to change the physics of my apparatus. So the physics of scale, of stretching and squishing, is not a symmetry of the universe, because there is a fundamental scale. The other way, when I was saying, like, the symmetry of time, there's no t equals 0. I guess there is when it comes to the Big Bang, but when it comes to experiments that I do in the lab, there's no t equals 0.
In the perception of the way we understand and see the universe, it's a little bit of a different context.
Yeah, that's a little bit in cosmology, there's a little bit of a different context, right? There is such a thing as t equals 0. Yeah. But in the scale of like experiments that I want to do in the lab, there isn't. There's no x equals 0, y equals 0. There's no like origin for the universe. So I can shift my experiment anywhere and the translation of space is going to work. But there is a fundamental scale, right? That has to do with like how big atoms are. If you want to get really, really nitty gritty about it, there's a fundamental scale that's the Planck length that has to do with like how big, how close I can get electrons before they turn into black holes.
Yes.
But there is such a thing, right? There's some meter stick.
Yes.
That's here. And so this is actually something that was first found by Galileo. In Galileo's dialogue concerning two new sciences. He published this thing. He had a really funny cartoon. He thought about like animals and what would happen if I had like a Clifford-sized dog.
Okay.
Remember Clifford, the big red dog? Yeah. So it's like I got a normal dog and then I got a Clifford-sized dog. What would happen? Well, the Clifford-sized dog, your mass, your weight scales like your volume, right? Mm-hmm. So it's gonna go like the length cubed.
Okay.
Right?
Yes.
How much stuff you have goes like length cubed because volume goes like length cubed. On the other hand, tensile strength goes like length squared because it has to do with the cross-sectional area of your bone.
Yeah.
You noticed that?
So I was just watching a video about this person hanging from rubber bands and seeing how many rubber bands it took to hold their weight up. And part of the discussion was about the tensile strength that is in the rubber bands in order to enable
exactly
holding it up.
Exactly. Like if he had if he had a chain of rubber bands, that wouldn't really help him.
Right.
On the other hand, if he had a bunch of rubber bands in parallel, that would help him.
Exactly.
Because the rubber bands in parallel would increase the cross-sectional area of how much is holding you up.
Bingo.
Right? And so Galileo has this really cool cartoon of like what a super dog bone would look like compared to a normal dog, where the normal dog is like this like small bone. This is one of his drawings. And then the super dog bone is just massive, but not so much scaled in the along the bone length, but like the thickness of the bone is way bigger.
The girth, one would say.
Exactly. The girth of that bone is way bigger, and that's where he scaled in. He's like, if I wanted a super dog or whatever, Clifford the big red dog, that guy's bones would be really thick because it needs to hold up the weight of the dog, right?
Yes.
I don't know why he chose dog, but anyways, maybe he had affinity to dogs. Who knows?
Look, I have 3 dogs, so I also have.
I love dogs. So yeah. I get it. If he had cats, he would not be my favorite. Nothing against cats.
Nothing against Schrodinger, but
I'm sure there's cat lovers in the audience. I'm just not a cat person. Okay, here's another broken symmetry, right? We can think about motion. Okay. What if I put my experiment, right? I'm doing some experiment, and then I put my experiment on a spaceship that is moving at a constant velocity. Actually, according to Galilean relativity and later Einstein's relativity, my experiment on that moving spaceship that's going in a straight line at constant velocity is going to have exactly the same results as my experiment that's on the ground that is stationary, whatever that means. Because turns out, if I can't tell in my spaceship, I can't do any experiment that tells me if I'm moving and somebody else is stationary, and so on and so forth, right? If both of our experiments are exactly the same, I can't tell who's moving and who's stationary. All I can say is somebody is moving relative to me. That was the big, light bulb of Einstein to say that that's actually true. What are the consequences of that, right? That's something called a Lorentz transformation. So that's a symmetry of the universe. The fact that I can boost myself into a reference frame where I'm moving in a constant velocity, but my laws of physics won't change. On the other hand, you can think, okay, what about if I'm rotating at a constant angular velocity? Is that a symmetry? What that means is if I'm in a spaceship that's just, let's say, stationary, whatever that means, and I do an experiment, and then I put myself on a rotating reference frame, for example, the Earth, right? But take out gravity. Somehow I'm rotating, but there's no gravity. Would the experiment be the same? The answer is no. The answer is no. And I mean, have you been to Griffith Observatory?
Yes.
Have you seen the big pendulum from the ceiling down? That's called Foucault's pendulum. That's a great example of a pendulum that is behaving differently because it's on a rotating reference frame. Because it's on a rotating reference frame, the pendulum is going to rotate within itself and knock over those little tiny thingies and like show that the Earth is rotating. That was one of the first big proofs that the Earth is really rotating.
And you're visually kind of showing like there's like this basin, right, where there's this pendulum that's floating. Like imagine a clock, but like it's now as the Earth rotates, the pendulum will move to different hours on the clock because that reference frame is changing.
Exactly.
Just in terms for the listeners, visually, like that's what you're describing. Is the rotation makes it so that if the pendulum starts going from 12 to 6, as the Earth rotates, it's now going from 1 to 7, 2 to 8, whatever it might be.
Yeah, exactly. And it goes at different it goes at different speeds based on how far up you are on the Earth in terms of latitude. So that is not a symmetry.
Right.
Okay? Like the fact that I can just I can't just take my experiment and start rotating it at a constant velocity. I can turn it and then do stuff. That gets me angular momentum, but I can't like constantly be rotating. Okay,
that's so interesting,
right?
Yeah.
So not everything is allowed,
right,
by the universe.
Right.
Okay, certain things are allowed, and certain things are not allowed.
The admin exposed some parameters that are tunable, but it's like not all of them.
Not all of it. Yeah, exactly. And so in the early 1900s, the question started becoming, what are the things that are allowed and what are the things that are not? We've already talked about how translation in space is allowed, so I can move my apparatus from here to there. I can move my apparatus in time, so I can do stuff here, I can do stuff tomorrow, and it'll be fine. I can rotate it, and it'll be fine. What about parity? Okay, the question is, are the laws of physics ambidextrous?
Mm-hmm.
Meaning, do the laws of physics distinguish left from right? Okay, like the Taj Mahal. The Taj Mahal does not distinguish left from right? I can flip the Taj Mahal in the mirror and it'll look exactly the same. If I put a giant mirror in front of the Taj Mahal, right? And then I got somebody to be in the garden of the Taj Mahal and he's looking one way and he's looking the other way. If the mirror is big enough and if he's not allowed to move around, he could not tell which one's the real Taj Mahal and which one's the fake Taj Mahal because the Taj Mahal is symmetric under inversion, right?
Mm-hmm.
The question is, can someone devise a physics experiment to show that we are not doing that? Okay, and this is something that I've borrowed from Feynman. He proposed a thought experiment. He said, suppose we're making a clock. Okay, we're making a clock that's normal, so it's going to go, clockwise.
Yes.
Okay, and now I make a clock with that looks like my grandfather clock, but in the mirror.
Right.
Okay.
So we're seeing an image with two clocks. One that looks like a normal clock, where the 12, the 3, the 6, the 9 look like normal numbers.
And the hand is going to go from the 12 to the
And then there's a second clock that's basically inverted.
It's the inverse. So the 12 is flipped. The 3 is where the 9 should be.
Yes.
The 9 is where the 3 should be.
Yes.
And then the hand goes from the 12 to the inverted 3
to the left. It's rotating counterclockwise
instead of clockwise, right? So he's like, can I make a clock like that? Okay. This was part of his Feynman lectures of physics, which I'm a huge fan of. So how do we make such a clock? Well, we got to be really careful. Okay. For example, even the screws, all of the screws are right-handed on our grandfather clocks, right? because in America and I think across the world, right? Righty-tighty, lefty-loosey. Yeah. I think that's just a standard all over the world now. Yes. But that's just a human convention. If I wanted to make a truly symmetric mirror image clock, I'd have to call up my guy and have him make left-handed threads, which is like probably super hard because the thingy that's making the thread is itself right-handed. Right. So he'd have to make like custom equipment and all. He'd probably have to 3D print or something like that. But if we did, let's say we went through all of that trouble.
Yes.
Okay. And we made a mirror image clock.
Yes.
Okay. Would that clock go exactly like the mirror image of my normal clock? And intuitively, it seems yes, right?
I mean, without thinking too hard about it.
Honestly, like it does seem yes. Honestly, why like not? If the gears are tuned different, if the screws are tuned different, if everything is reversed, then of course the clock is going to go in reverse, right? And that was the way to do it for the longest time. And another way to think about this parity symmetry, right? We just talked about like the clock is really a microcosm of like, can I make an experiment that goes one way or the other, right? That can tell the difference. If the clock does in fact do something different, then that means the universe does care about left or right? But in this case, I mean, we're pretty convinced that like the clock is gonna, right? All it's relying on is gravity if there's a pendulum, and then like electromagnetism, which is just like the atoms pushing up against other atoms to like make the gear turn, and you got some motors. I guess not a motor, right? Because the pendulum is providing the. Yeah. In any case, it seems like it should work. Another experiment that I thought was really cool that I found in his lectures was the alien thought experiment. Okay, so here's the challenge. You're on the phone. Somehow the aliens have contacted us.
Yes.
Okay. This is your dream come true.
Look, I'm trying to set it up.
Yeah.
I'm trying to set up the group chat right now.
Yeah. Yeah. So, okay. Imagine we're on a group chat. Okay. We can't send them any photos.
Okay.
Okay. All we can do is like chat with them.
Okay.
They're on some really far away planet.
Okay.
All right. How do you explain left or right to them? If there was somebody in LA, right, it would be pretty easy to explain left or right. You could just like tell them to look at the Hollywood sign, for example, and then be like, the H is on the left of the D. Easy. Easy clap, you're done. They don't have the Hollywood sign. Okay. So what do? Well, you could, if they're on Mars, then they're still in our local neighborhood.
Yes.
So you could tell them to look at the constellations.
Yes.
Right? You could be like, oh, look at the Big Dipper. And then you see how there's like the four that are kind of in a rectangle-y, like they're to the left of the handle. Okay, great. Yeah. So now you've defined left or right. Now suppose they're in a completely different galaxy and somehow we've had a wormhole that lets us text, the texts are going through the wormhole. Okay? How do we tell them? How do we tell them? Feynman puts out a really funny, like little failed attempt that I thought was interesting enough to highlight here. Okay, so he said, okay, well, if I take like sugar molecules, like from sugarcane or something, and I dissolve it in water, and then I have plain polarized light, that's something that I can tell the alien how to make, right? Let's say they understand English. They just don't understand left and right. I can tell them, a plain polarized light, meaning like, you guys know what light is, yes. And they'll be like, yes. And I'll be like, okay, you guys understand that there's a polarization where the electric field is in one direction and the magnetic field is in the perpendicular direction. They're going to be like, yes. We're going to be like, okay, so let's get plain polarized light, which means all of the light has the electric field moving in one direction. And they're like, okay, cool, I can do that. Seems like something they can do. And then we're going to be like, okay, get a bunch of sugars. Sugars meaning C6H12O6, glucose. Okay? Get a bunch of sugars and then put your plain polarized light through the sugars. Okay? And what's going to happen is as the plain polarized light goes through these sugars, it's going to rotate. It's going to rotate. And this we've got a little visualization here.
Yes.
It's going to as the plain polarized light goes through, the electric field, which is only moving up and down, that's how we prepared it. It's going to start rotating to the right.
Okay. Yes. And
so you can tell your alien, hey, okay, so just watch how your light rotates through this sugar water thingy. Okay, and then the direction that the light comes out, that's the right.
That's the right.
Okay, and the other way is the left.
Okay.
Okay. Seems pretty cool.
I'm tracking.
Seems pretty good. The problem is the sugars that we make on Earth all have a certain chirality because the sugars are a C6H12O6 ring. There's a ring of carbons, right? It's a little hexagon of carbons and oxygens. And the way in which they're arranged are always in one particular handedness. Okay, you gotta go clockwise to see the way that the elements are formed. But you could make sugars in the lab
that
are the exact opposite direction.
The chirality is the opposite.
Okay, the chirality is opposite. It's just that all of life on Earth, for some reason, makes one-handedness of sugars, and that has to do with the fact that all of the proteins that we have on Earth have one-handedness. Okay, so there's proteins like all of the primary amino acids in life, right? Except one, glycine, are chiral, and so there's isomers of these amino acids where you've got the D isomer and the L isomer, the left-handed form and the right-handed form, and most of our amino acids are the left-handed form. Okay, it just is what it is.
Right.
Because there's actually this is a big mystery in like the origin of life. Like, how does everyone like in the same? You could have picked two, and everyone's picked one, right? And it's probably because whatever primordial ancestor was the first, primordial origin of life on Earth picked the left-handed form, and then as everyone descended from that, right, the DNA became left-handed, the proteins became left-handed, the glucose that comes out becomes a certain handedness, everything becomes that handedness. And so you can make stuff in the lab, that is both, right? You can have both chirality in the lab, but when it comes to biology, we're always going to make one-handedness.
That is fascinating.
So if we're talking now, we're DMing this alien, right?
Yes.
And we're like, make a bunch of C6H12O6.
Yes.
He's actually going to be like, I'm getting both. I'm getting stuff that's going to the right and to the left. And we're going to be like, okay, which one can you eat? Right? He'll be like, oh, maybe he could eat the ones that are left, because the primordial life on his planet was the other handedness, right? So that's not going to work.
It's not going to work.
I thought that was such a cool little...
That's very...
You know?
And it's such a simple question that has such deep implications in terms of actually trying to facilitate. It starts off like a silly go, like, oh, how can you tell an alien with left versus right?
Yeah.
But there's actually some really deep fundamental...
There's deep physics here.
Yeah.
Can you?
Yeah, can you?
The question is, can you?
Can you?
Can you... without sending him a photo.
Right.
If I send him a photo, it's easy.
But via
just strictly, I need you to do stuff there.
Yes. In order to illustrate left versus right.
Left versus right. Can I do this? Right? So it's still failing, even if we do these this chemical sort of... Okay, so the chemistry is failing. Right? All right, now let's do a physics attempt. Okay. In physics, we're always talking about something called the right-hand rule. Okay. Right-hand rule is how we do cross products of vectors, and it defines our coordinate system. For example, if you have a wire that's got current moving up, then you put your thumb on your right hand towards the current, and then you curl your hand. And the way you curl your hand is the way that the magnetic field is going.
So in this image, we're seeing someone with a thumbs up hand with this wire going through it,
and the current is going up.
The current is going
up. So the thumb is pointing up,
and there, you can see the hand. The fingernails are in the front of the image. Yeah, and so the
way that I curl the fingers
are curled counterclockwise.
Yes,
and and then it's also now flowing.
The magnetic field is flowing where my fingers
are, which is this.
So that's called a right-hand rule, and we live in a right-handed coordinate system. Okay. What that really means is the following. Okay, what that means is if I have my x-axis, let's say this way, and my y-axis this way, then my z-axis is this way.
So if I have my x-axis pointing north,
let's say pointing outward, and my y-axis to the left, then the z-axis is up.
Okay.
Now, somebody who created physics could have easily been left-handed, and said, "Nah, x-axis this way,
outward,
y-axis this way, so z-axis is pointing down." The fact that z-axis is pointing up here and not down is just a human construct.
It's a choice.
It's a choice that we've made because probably the guy who made up the cross product was like, "I'm going to use a right-handed coordinate system," right?
Yes.
And so our coordinate system is right-handed just by pure choice, but we could have had our z-axis pointing the other way, and it would have been the physics would have been completely fine.
It's the same.
It's the same.
It's just this orientation.
So we can't really use physics, right? And to illustrate this further, right? Let's think about what happens to like motions of particles and vectors in a mirror world. Okay. So if I have a mirror that's right in front of me, and I have a particle that's moving away from me.
Yes.
I would go to the other photo.
Yes.
If I have a mirror in front of me, and I would go, let's say the particle is going towards the mirror. Okay. So it's moving away from me.
Yes.
In the mirror world, what I'm seeing is the particle would come towards me.
Yes.
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 So the trajectory of the particle is flipped.
Yes.
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 Okay. But if I have a current that is now, let's say I've got a current that creates a magnetic field. All magnetic fields are created by currents, right? So if we go to photo 11, we'll actually see on the left-hand side, we're going to see a current that is twisted to the right. Okay. So in our world, it's twisted to the right, which means that if I were to follow this loop of current, right? Let's say I make a loop out of the current and it's twisted to the right. So my right hand is following the thing, then the B field is pointed up.
Yes.
Right. But in the mirror world, that current would be pointed to the left. And so the B field would be pointed down. Right.
Yes.
And everything in physics has to do with everything when it comes to magnetism and charged particles and how those charged particles move in a magnetic field. In physics, that has to do with the cross product of my velocity and my magnetic field. But what just happened is I just flipped both of those vectors, right? The velocity became the negative.
Yes.
And the B field also flipped.
Yes.
So I got a negative times a negative, which becomes a positive.
This is okay.
Right?
Yes.
So I can't do it. I can't like.
Yes.
I can't actually do it. With just pure electromagnetism?
You cannot explain to the Martian what is left versus right because of this like mirror symmetric.
Yeah. Because all of the laws of physics so far
are
exactly mirror symmetric.
Right.
Everything in the mirror world is the same as my world.
Yes.
There's no way for me to DM him and explain to him what is left and right.
That's so
It's so cool to think about, right? So we've tackled gravity. Gravity doesn't care.
Yes.
Gravity really doesn't care.
Yeah.
Electromagnetism we thought kind of cared because we're always worried about the direction of the magnetic field and like the crossing of the products and but it turns out like in the mirror everything is flipped. So the motion of the particle isn't actually going to change. Right? So we're really in a conundrum here.
Right.
Like, how are we going to tell this guy?
Right.
How are we going to explain to this guy the simple fact that like my heart is on the left-hand side?
Right.
You know?
Right.
And I write with my right-hand side.
And what does that actually mean?
Yeah. Does it mean anything? It becomes a very philosophical question, right? Does it mean, like, is there really no difference between left and right? Does the universe really not care?
Well, if we're talking about politics, there's certainly a difference between
there's certainly a difference,
but
right?
Maybe that's why we shouldn't be labeling them in these directions, because in physics there's
it seems there's no difference.
Or maybe this is where horseshoe theory comes from.
It's the same. Yeah, exactly. Yeah. Exactly.
Anyway.
So we've been discussing this question, right? Is parity conservation a law of the universe? And so far it seems yes. Okay? Meaning that if I have some experiment and I do some experiment, and then I do the mirror image of that experiment, the results of the experiment are exactly going to be the same. Okay, so let's review a few things, okay? Certain vectors flip sign. Okay? Like position, for example. If I'm moving in this direction, in the mirror image, it's going to flip sign.
When you say this direction, how do you mean? Just for
for example, like, let's say there's a mirror in front of me. Okay. If I'm moving towards the mirror, in the mirror world, that particle is going to be moving towards me.
Got it.
Right? So it's like I'm moving towards the wall. Let's say the mirror is on the wall and the particle is moving towards the wall. Well, in the mirror world, the particle is moving out of the wall, right?
Yes.
So it's flipped its sign.
Yes.
Right? That's what parity means. We're flipping all of the x's. X becomes negative x, y becomes negative y, z becomes negative z. Okay? Now, certain vectors, these true vectors, they flip their sign. But then there's other vectors called axial vectors that do not. For example, angular momentum. Suppose I'm doing this with my hands.
Rotating in a clockwise direction.
Yeah, rotating in a clockwise direction. So the spin is towards the wall.
Okay.
Right?
Yeah.
It's towards the wall, into the wall.
Yeah, the righty-tighty idea.
Yeah, righty-tighty idea. Well, that rotation is going to look the same in the mirror world, right? In the mirror world, if I'm doing my hand like this, the mirror's trajectory is also going to be going clockwise. So in the mirror world, that the spin is going to be going into the wall, right? It's going to be going like the angular momentum actually doesn't change.
Wait, this is actually
it's kind of trippy.
crazy.
I really need you to focus here and think about this.
That's actually really crazy, because what you're basically saying is in the mirror.
Look, and if
pull it back up.
We pull it back up. Like on the left-hand side, we've got a wheel that's turning like this.
Yeah.
And so the spin vector is to the right.
Yeah.
Now I flipped it along the middle. It's spinning, but the spin vector is still right, because it's like imagine I got a mirror in front of me. I'm doing this. In the mirror world, that thing is, my hand is still doing the same kind of thing.
Yes.
It's because I've changed both X and Y to be negative and negative. And the spin is a product of those two coordinates. So the negative, it's still going to be pointing in the same direction. So an electron that's spinning this way into the mirror is going to be still pointing, like going the same direction in the mirror world.
In the mirror world.
This is a crucial thing for you to understand.
I've never
right. And can you imagine it?
No, so I can in my head.
Yeah.
No, I can. I can
it's
visually.
Crazy.
And it's making me uncomfortable because it doesn't make sense.
Yeah.
Like, but not even that it doesn't make sense, but it's the distinction between the first use case we just talked about of the position vector, like versus this axial vector, and simply like it seems like such a simple difference.
Yeah.
But the implications of that simple difference are change everything.
And the real underlying substrate here is that axial vectors are not true vectors. They're kind of like they're products of two vectors, right? Angular momentum is r cross v. So because you put a negative on one and the negative on the other, it's going to be the same, right? The position vector is literally like, where am I going from where I went to?
It's flat,
right?
There's no dimensionality.
There's nothing tricky about it.
Right.
But when it comes to axial vectors like angular momentum, those things do not flip.
I'm like, I have so many thoughts.
Yeah, it's crazy, dude. So this is central to the idea. Okay. Some vectors change, other vectors do not. When it comes to parity. Mm-hmm. In the mirror world, right? If my angular momentum is that way, in the mirror world, it's also going to be that way. On the other hand, if my position is this way, the guy is coming at me, right? If I have like a bug that's flying away from me towards the mirror, then that bug is flying towards me out of the mirror.
Yes.
So the position vector is flipped. But if my bug is like rotating like this, it's going to be coming towards me, but it's going to be rotating like.
Yeah.
So the position is, but it's still going to be rotating in that same clockwise way.
Yes. And it's actually like really trippy to think about.
It's really trippy to think about, dude.
Okay, I'm tracking. No, I mean, this a total side note to this, but this kind of reminds me, it's not similar, but there's this gentleman who's created this thing called the true mirror, because we're seeing a reflection, a mirrored version of ourselves when we look in a mirror versus what other people see when they look at us.
Yeah.
And there's actually this like physiological response that we as humans have when we see a mirror reflection of ourselves versus like what other people see of ourselves. And so like, because your brain processes the mirror image in a certain way.
Yeah.
And so when you see it in the opposite, there's like these outcomes like, oh, you tend to like not be gazing in the eye, like trying to find the eye line. You naturally like are not uncomfortable and smile. Like there's this whole like arena of stuff. It's not the same thing, but it makes me think about that use case because I've never before thought about the idea that the way people see me in the world is not the same thing that I see in the mirror.
No.
And so everyone sees me the reverse of how I think my existence is.
Yes.
And that's very weird.
Yeah. They're seeing just like, I guess you. I don't know. There's no flipping.
There's no flipping
because flipping is a crazy thing, right? You're flipping axes and all this other stuff.
But if I was like having angular momentum towards me, anyway.
Yeah, exactly, dude. It's crazy. It's crazy to think about.
It's very,
but my main point here was some vectors, like my velocity, like my position, those are true vectors. Those are going to flip sign.
Yes.
My angular momentum is not going to flip sign.
Right.
Okay?
Right.
Now, we start getting these weird experiments from Otto Laporte. He's a student of Sommerfeld. Sommerfeld we've talked about at the University of Munich, one of the great physicists of Germany before the war, who tutored the likes of Heisenberg and Pauli and all these people, never got the Nobel Prize. But he showed in experiments with iron that if you have, you know how like in quantum mechanics you have transitions between energy levels
Yes.
of an atom. The electron is in some energy state and then it goes to another energy state, and
they're discrete.
Yeah, and they're discrete. And when that transition happens, it lets out light, and by measuring the light, you can tell what kind of transition that happened.
Yes.
Well, he found that there's certain transitions that never happen.
Okay.
Okay. If the electron is in some state, it's never going to go to some of these other states. Okay. And Eugene Wigner created these things called selection rules. Okay. Turns out that atoms have two kinds of energy levels. There's one that has even parity, which means that if I flip the coordinates, it's the same. That's the one. Like if it's symmetric about the y-axis, right?
Yes.
And if I flip, it's like the Taj Mahal.
Yes.
And then there's another one where if I flip the parity, it's going to be the negative of that. Yes. It's like a flippingness of the Taj Mahal. Okay. Yes. But there's one state that looks like the Taj Mahal, and then there's another state that looks exactly the opposite.
Yes.
Okay.
Yes.
And what he found was that when these electrons switch energy levels, they have to conserve parity. Okay? One of them is even, the other one is odd. You can assign them numbers that are even and odd. And the total parity before has to equal the total parity after. So it became, and everybody liked it, right? It's like, okay, it's like intuitive, right? If I made a clock that's in this opposite mirror world and it works the same way, conservation of parity comes from Noether's theorem. Yes. So it's all nice.
It's all tracking.
It's all tracking. The universe can't distinguish between left and right. We're in a nice universe that's just agnostic about what is left and right. It doesn't care. Okay? Then comes the puzzle of the theta and the tau. Okay? These are mesons. Mesons are, at the time they didn't know what it was, but this was, now we know that a meson is basically a quark and an anti-quark bound together in a single particle. At the time we didn't know what it was. In the 1950s, these physicists, they found two particles, the theta and the tau, okay? And they were the same in every regard, okay? They had the same mass, they had the same charge, they had the same lifetime even. The lifetime part is weird, okay? Because they got the same lifetime, but they're different in one tiny thing, okay? And the one tiny thing is in how they decay. One of them decayed into 2 pions and the other one decayed into 3 pions. It's not important what pions are. The main point is pions carry a parity charge. Okay, you know how I was saying that we can assign parity numbers to our states? Yes. Well, pions have parity numbers. Okay. And all of a sudden, you had 2 identical particles in every other aspect, but one of them had a different parity decay, and the other one had a different parity decay. Okay, one of them was going into 2, the other one was going into 3. So one of them had an even parity, and the other one had an odd parity. If you think that parity is the same, right? On the left-hand side, we've got the theta, which is, on the left-hand side, we've actually got the tau that's going into 3 pions. And on the right, we've got the pi that's going into 2, right? That this is just a schematic diagram showing like that decay.
Yes.
This is very weird.
Yeah.
Because if the law of conservation of parity is true, which everyone assumed it's true, then the decays must end in the same parity. But here we've got the same particle that looks pretty much the same.
But they have
in every aspect. But they have this diverging decay.
Parity decay.
Okay?
Okay.
And so now it's like, how could these two be so similar and yet have such a different thing?
Right.
One possible resolution is that these are 2 very different particles.
Okay.
The other possibility is that these 2 are the same particle, but parity is not conserved in this process.
Okay.
And all the stuff that we've talked about with electromagnetism, with gravity, parity is conserved. But in this particular thing that we are observing, it is not.
Okay.
Okay?
So the conservation of parity is not universal.
Yes. Maybe not all the laws of physics obey the conservation of parity. Maybe there's an exception.
Okay.
Maybe gravity is not the exception. Maybe electromagnetism is not the exception, but maybe there's something else. Okay? And this is where the hero of our story, Yang Chen Ning comes in. Okay? So Yang Chen Ning, born in 1922 in Hefei province in China. His dad was actually a professor at Tsinghua University. in Beijing. He was a math professor. He's one of the few people who actually did his PhD outside of China and then came back to teach in China. So he's had exposure to group theory from a very early age. Group theory is the mathematics of symmetry. Okay, so he's gearing up for this fight early on, right? He's forged in war, actually, like during the Japanese invasion of Kunming in 1937. This was before the all-out break of war in the Pacific Theater, where the United States got involved after Pearl Harbor. The Japanese were doing all sorts of random, stupid nonsense, terrible stuff in China. And so all of the Chinese academia actually went down to Lianda in the southwestern province, and they sort of conglomerated all of their academic might in the south away from all of the fighting. And this is where Yang Chen-Ning did his undergraduate and his PhD. Okay. No, sorry, not his PhD, his undergraduate and his master's. Okay. And he actually learned about quantum mechanics at a very early, even back then. I mean, it's quite remarkable because quantum mechanics was still quite early, but the university was so good that he was already getting exposure to quantum mechanics at that early undergrad master's level. He gets on one of these Liberty boats from China to the US. He caught it in Calcutta, actually. These are boats that were set up after the war to bring in people from the Indonesian, Indo-Chinese theater that was happening in Burma to the United States. So he goes through Calcutta, through the Red Sea, through the Mediterranean to New York. There were no direct boats to San Francisco. So he actually had to come the other way, all the way around the earth, right? He ends up in New York. He stays. I was just watching some of his interviews from Stony Brook University, which is where he ended up and spent a majority of his academic career. They have these incredible interviews of the man, Yang Chen-Ning. And he was talking about how, like, you know, when he first got off the boat, he got a hotel room in Times Square, which back then is not now it's like all touristy, but like back then, it's sketches.
Yeah, not the same thing.
It's not the great thing.
Had it pre-gentrification.
Yeah, so like his first exposure to America was Times Square in the 1940s. Anyway, so he gets there. He goes to Columbia in search of Fermi because Fermi was officially on the roster of Columbia. He goes there, he asks the secretary about Fermi. The secretaries don't know who Fermi is because I don't even know. Yeah. Fermi was at the time, he was never in Columbia because he was doing classified research for the government for the Manhattan Project. But I mean, come on, you don't know who Fermi is? Anyways, all right, fine. He goes to Columbia, he can't find Fermi. He goes to Princeton, he actually meets Eugene Wigner. There, Wigner tells him that he's going to sabbatical at Oak Ridge, which is another classified thing. Because Yang Chen-Ning is Chinese, you know, you can't. You're not gonna get a job with Wigner.
You're not gonna get read into the special access program.
No, it's like you just got here. You know, it's like
especially at that time.
At that time, it's like we don't know.
It's tough. It's tough.
Yeah, it's tough. So then he goes talks to Wheeler. Wheeler, someone that we talked about, another Princeton great. Wheeler gave him some problems. Those problems didn't really interest him. He tried as much. And then he got word that Fermi was actually permanently going to Chicago, University of Chicago from Columbia. And so he applies there. He sends a telegram to Chicago. Gets in immediately because his grades were so good in the Chinese undergrad and masters. So he gets in. He goes to the Chicago school under the guidance of these giants, Enrico Fermi, Edward Teller, the villain of the Oppenheimer movie. He actually got his PhD under Edward Teller.
Okay. Oh, very interesting.
Edward Teller was his PhD advisor. And that's actually a really funny story because he wanted to at first get his PhD under Enrico Fermi. But Fermi had gone to Argonne National Lab, again, for classified research.
Yes.
Right? So he's like, I can't really take you. I'm really sorry. He goes to Teller. Teller gives him problems. These are problems that aren't really interesting to Yang, right? So Yang's trying, couldn't solve them. He's like, okay, maybe I'll try my hand at experimental physics. Fails miserably, like every theoretical physicist does who tries to go into the lab. Just has no idea what he's doing. In his interview, he's actually talking about how the graduate students would like literally laugh at him. But they were like also best friends with him because he would solve their theoretical problems,
Right.
But he was just hopeless in the lab.
In the lab.
Right? So he's there for 3.5 years just doing nonsense, breaking shit. And during that time, he publishes independently some papers about the symmetry groups and group theory and how that can be applied to nuclear fission and nuclear decay. Okay, this catches the eye of Teller again. And Teller comes up to him and he's like, so at this point, he's kind of, famous in the University of Chicago because there's not a lot of Chinese students, not like nowadays when there's so many Chinese students in American universities, so many international students in American universities. Back then, there's few and far in between. And he's so good at theoretical physics. So, and he publishes these papers. So Teller comes up to him and he's like, so I heard you're doing pretty bad in this lab. And he's like, yeah, man, I'm really struggling. But Teller says, I liked your paper that you put out. If you want to submit that as part of your thesis, I'll be your advisor. Because this was something that Teller hadn't even thought about, Edward Teller. But he's like, this is interesting stuff. So if you want to, graduate with a PhD under me, just like make it a little bit longer. It can't be like, I can't submit like a 3-page paper as your thesis, but I could talk if you're doing like a little bit longer. He comes back with a little bit longer paper. Teller's like, this isn't long enough. Like, I was meaning like substantially longer.
I was trying to be nice.
Yeah, I was trying to, like so Yang comes back with a longer paper, and Teller's like, all right, this is fine. Actually, at a later celebration of Yang's birthday, Teller went up to speak, and he talked about how the third submission that Yang had of his paper was still too short, but he was just like, this is hopeless. Like, this guy's clearly a very good physicist. Let's just I'm just gonna talk to his. I'll go to bat for him. It's
look, having Edward Teller go to bat for you is not not a bad thing.
It's not bad at all. 1948, he gets his paper. One of the cool things about his time at Chicago was he was actually in a 2-person class with Tsung-Dao Lee under the tutelage of Subrahmanyan Chandrasekhar. Okay, Subrahmanyan Chandrasekhar is one of my heroes personally. He's somebody that Subrahmanyan Chandrasekhar is one of the heroes of Indian physics. He discovered the Chandrasekhar limit, which is the white dwarf limit, how big a star can get before it can no longer be a white dwarf. At the age of like 19 or 20, he discovered this. He faced intense racism in Great Britain by someone by the name of Arthur Eddington, who himself, great physicist or whatever, but whatever.
Gatekeeper, we get it.
Yeah, we get it. So he was hired by the University of Chicago, and at the time he was working at the Yerkes Observatory in Wisconsin. He offered this course. I forget what the course was actually, but only 2 people signed up. It was Tsung-Dao Lee and Yang Chen Ning. Okay, he would drive 200 miles from Yerkes Observatory to Chicago every week to do this course and teach this course. But good thing for him, because that course holds the world record for number of Nobel Prizes. 100% of the attendees of that course, 100% of the attendees of that course won the Nobel Prize. No other course has that, because he got 2 students and both won the Nobel Prize.
So crazy. That's actually pretty crazy.
That's a great, like that's a record that I don't think it's ever going to be beat.
We're gonna put that in the stat locker for FFP when we start the leaderboards.
Oh, that'll be a great one. Yeah, it's like classes. Yeah,
we're gonna build out a stats library just like all major professional sports do for when the announcers like, oh, this is the last time we saw 300 yards, 42 was in 19
Yeah,
we're starting the same stats library, next gen stats.
Yeah, next gen stats, and that's gonna be one that's like never gonna be beat. Okay, you had 2 students, both won the Nobel Prize. 100% Nobel Prize winner class. Imagine, right? Yes. So Tsung-Dao Lee is actually instrumental in the next part of our story.
Okay,
because Tsung-Dao Lee and Yang, they are the ones who start looking at that tau theta puzzle that we were talking about, right? You got these 2 identical particles, they're decaying in weird ways.
The parity, there's no conservation of the parity because they're decaying into 2 and 3.
Yeah.
Which is weird because there's like same size.
Yeah, same, but different. But why are they different?
Why are they different?
Like, is it that they are different, or is it that the laws of physics are a bit different?
Are not the conservation of parity has exceptions.
Exactly. Yeah.
Okay.
So Yang and Lee, they propose a revolutionary idea. What they do is they go back and look at all of the literature. Okay, there's a funny story here where they were in Colombia at the time, and they're searching for parking, and they're in the car. He talks about this in his memoir. They're in the car discussing this issue of the theta and the tau, and they're like, "Is parity conserved? Like, what's going on?" And they have this idea, but they're looking for parking. They can't find parking because it's Manhattan. There's no parking in Manhattan. So they park in this like restaurant, this Chinese restaurant that hadn't opened yet, but like, they still, the restaurant had parking. So they find parking, they go into a cafe, and they continue their discussion. Mm-hmm. And what they're really focusing on is, has anyone actually checked if beta decay obeys parity? There's been all of these experiments to check that electromagnetism obeys this mirror rule. There's been all of these experiments to show that nuclear stuff, like the strong nuclear force, obeys the mirror symmetry. But has anyone actually done it for the weak nuclear force, which is what's involved in beta decay? Mm-hmm. So they decide to go through the literature, and they actually find out, no one has said one way or the other whether beta decay obeys the parity conservation law. Mm-hmm. So they write up a paper, and they actually talk about certain experiments that you could do to maybe find out if beta decay is different in the mirror world.
Yes.
Okay?
Yes.
Everything else is the same.
Right.
But beta decay is something that no one's actually bothered to check. Mm-hmm. Okay? They contact Chien-shiung Wu, who is an experimental physicist at Columbia. She's one of the great experimental physicists of the 20th century. And she was basically the expert in the entire world about beta decay and beta decay spectroscopy. So they're like, there's one person that we can go to, and it's Chien-shiung Wu. Mm-hmm. They proposed this idea, this like, I want to check if this thing is symmetric. So Wu comes up with this ingenious experiment. Okay. Here's what she does. She gets cobalt-60, which is an isotope of cobalt. Okay, it's got 60 neutrons and protons in its nucleus. And what they're going to do is they're going to wait for the cobalt-60 to decay into nickel-60. So notice, the atomic number has remained the same, which means what's happened is a neutron has turned into a proton. A neutron turning into a proton, that's a neutral charge going into a positive charge, which means it has to release a negative charge.
Release the negative charge.
Exactly. By the conservation of charge, the charges before and have to remain the same.
Right.
So if I've created a positive charge and I started at 0, I need to create a negative charge to balance it out. Mm-hmm. So this is a process of beta decay. Okay. This is something that has to do with the weak nuclear force. Okay. The question is the electron that gets spit out, does it have a preferred orientation?
This goes back to our right-handedness, left-handedness thing.
Exactly.
Okay.
Does the electron that gets spit out, does it have a way of only preferring left or right or one of the other?
Yeah. Right.
That's the question. It's a very simple experiment.
Yeah.
Right? And this is the genius of Wu. I mean, the experiment sounds simple. It's insane, right? You gotta get these cobalt-60 atoms, then you gotta cool it down to near absolute 0 because you don't want the cobalt-60 to be, right? You want to tell which way the electron is moving. So you got to collimate all of the cobalt-60 so that it's all oriented in the same direction. The cobalt-60 itself has a spin on its own, right? So you want all of the cobalt-60 atoms to be oriented in the same direction, which means you got to cool everything down to near absolute 0. Mm-hmm. This is something like 10 millikelvin, which is like difficult even now. But back then, like she had to do it at the NIST, the NIST offices in Washington, D.C., because they were experts at making really, really cold things. So she actually told them, this was in December of 1957.
Okay.
Or 1956, actually. December of 1956. She goes down to Washington, D.C., and she sets up this apparatus. She wants to do it fast because she knows this is going to be big. So she's like, no, I am Lady Wu. I am in charge of beta decay everywhere around the world. I'm going to do this. So she gets cobalt-60, she cools it down, puts a magnetic field on it so that all of the cobalt-60 atoms, let's say, are oriented in this direction, let's say away from me. So they're pointing in this direction. And she waits for the electrons to come out, right, during this decay. Now, here is the critical thing. Okay, there's two scenarios that could happen. The cobalt-60 is oriented in one direction. The electron could go forward or it could go backwards, right? If my cobalt-60 is oriented in one direction, the electron could spit out forward or backwards.
Yes.
Now, they're always going to be, the spin is always going to be oriented in the same direction as the cobalt-60 because of conservation of angular momentum, right? Like the cobalt-60 has an initial angular momentum that is away from me.
Yes.
So the electron that's going out is always going to have an angular momentum that's away from me. The question is, the direction of motion, is it going to be away from me or towards me? Those are the two scenarios, right? And in a world that doesn't care about left or right-handedness, both of those directions should be exactly equally probable. Right? I should have an equal number of electrons coming from the front as from the back.
Yes.
Because I've oriented the cobalt in the front direction, let's say. But if the world doesn't care, then the electrons should come out from the front and from the back equally likely.
Yes.
Because they're all oriented. I mean, sure, the electrons are all right-handed orientation, but if the universe doesn't care about right-handed orientation, then the front and the back should be equally likely. That is not what she saw.
So, okay, got it.
All of the electrons came out from the back.
Interesting.
All of the electrons came out from the back.
So the universe does care.
The universe does care.
That's so funny because after all of that,
yeah, but it's insane.
It does actually matter.
It does actually matter. Left and right-handedness is something that the universe does care about. This is a schematic. You've got the magnetic field in one direction. The cobalt-60 is oriented in that one direction.
Yeah.
There's two possibilities. The electrons going out front and going out back, but the electrons only come out the back because they're constrained by which way they can spin.
Okay.
Right? So if I could spin this way, I can only come out this way. In some mirror world, let's say that I have an anti-cobalt made out of anti-protons and anti-neutrons, and the thing that's coming out is a positron instead of an electron. Then it would come out the front.
This goes back to the same analogy of like when we're looking at the mirror, it's the same direction. It's okay. So let me take a step back.
It's crazy, dude.
So the experiment proved that there's not symmetry in the mirror image.
No, the mirror image physics is different. From our image. Yeah. Let me get a little bit more specific.
Okay.
Let me get a little bit more let me say it this way. Okay? I've got my cobalt nucleus, right?
Yes.
My cobalt nucleus is in this direction. It's spinning clockwise.
Yes.
Right? In my mirror world, the cobalt nucleus is also spinning clockwise.
Right.
Yes?
Yes.
Okay. So, in my world, the cobalt nucleus is spinning clockwise, but the electrons are shooting out towards me.
Yes.
Right?
Yes.
In the mirror world, if everything was exactly symmetric, the electrons should be shooting towards the mirror Krishna.
Not towards you.
But it'd be coming towards the real Krishna.
Right. Yeah.
The physics is different.
The physics is
You see what I'm saying?
Yeah.
Because the spin of the cobalt hasn't changed in the mirror world.
Yes.
But if the physics is the same, the electron coming towards me in the mirror world, the electron should be going that way.
Yes.
But they'd be coming back this way.
Back this way. So there is not this conservation of parity.
There's not a conservation of parity when it comes to beta decay.
When it comes to the weak nuclear force.
When it comes to the weak nuclear force.
Specifically. So it's one of those things where there is an exception specific to, not to gravity, not to the strong nuclear force.
Not to the electromagnetism either.
Not to electromagnetism either. But the weakling,
the weak nuclear force
does not have this conservation law that is true everywhere else, which is fascinating.
That's crazy.
No, that is crazy.
That is, dude, it's like, because now we can DM our aliens.
Right.
We can DM our alien and be like, hey, prepare some cobalt 60. Right? And then orient it in whatever way you want. So orient it in whatever magnetic field you want. And the electron that comes out, the way it's going to come out. Now pretend the electron is going out this way. Then the way that it turns, the left hand, my heart is on the left, the way that it turns.
Yes, is left. This was Feynman's original Martian problem.
This is Feynman like talked about all of these things in the context of this Martian problem. In his Feynman lectures.
And this is the actual solution to how can you tell the Martian left or right?
Yeah.
Is you can use beta decay or the weak nuclear force as the one area where there's an exception to the conservation of parity as the methodology by which you can communicate left-handed,
and now we can do that by simply describing an experiment. Right. This is huge.
Right.
It means the universe does care.
Okay. Yes.
About left and right.
Yes, which is so funny.
That's crazy.
In the story arc we got to get there. And again, this goes back to why from first principles matters so much, because people don't just like make things up out of whole cloth. Mm-mm. You know what I mean? There's this decades-long conversation that's going back and forth, and people are really thinking about the fundamentals and creating experiments in which to be able to say yes or no. And a lot of times it's fail. It's not a success until someone like Wu, in this case, creates that experimental design that just perfectly...
It's just perfect, and there's no bells and whistles. Right. It's like so obvious.
Right. In retrospect.
In retrospect, it is, yeah. It's really unfortunate, actually. She didn't win the Nobel Prize for it. Tsung-Dao Lee and Yang won the Nobel Prize, and it really should have been a 3-part Nobel Prize. And it is one of the most... It's a real shame. It's the one that almost every physicist agrees, like without a doubt, Wu should have won that Nobel Prize. Because there's no Tsung-Dao Lee and Yang without Wu. Actually proving it.
Right. Like that was what created the actual experimental.
Yeah. And like people like Paul Lee were pissed off about it. Wigner was pissed off. Like everybody in the community was like, "What are you guys doing? That you didn't give it to Wu?" It was almost So it was really unfortunate, for this giant of physics.
A seminal figure.
Like there's no, like even, you don't have to, it might be because she was a woman, probably, honestly, back then in the 1950s at the time.
Yeah.
Probably. It's so unfortunate because, it's like clear and obvious how big of a deal this is, right?
We need VAR for the Nobels.
Yeah.
Because that was a clear and obvious error by the officials at the time.
And at the time, like this was in December, she, took off her holidays.
Yeah.
She canceled her holidays to do this experiment because she knew how big it would be. Right? I mean, and in January, when all of the results came out, even before the paper was published, everyone in the physics community was talking about it. They were writing letters to each other. It was by telegram. The paper was under peer review, but it spread like the new gospel.
Yeah.
That parity is no longer a rule in the universe.
Which is a big...
That's a big deal,
That's a big
dude.
deal.
That's a big deal. Because parity had that pedestal that was the same as translation in space, translation in time,
conservation of energy.
Yeah.
Like, imagine if someone rolled up the it's like, oh, the conservation of energy actually
is not a thing.
It's not a thing. Like...
Yes, that would be like, yo, what are you talking about?
It would be a huge...
It would be a huge deal.
It would be a huge deal.
Yeah. It spread like wildfire across the world, through the telegrams. So it's really unfortunate that she didn't win the Nobel Prize. And that is what won Yang the Nobel Prize.
Right.
Okay? What he's most known for actually nowadays, and I'm just going to go through this real quick because I don't have the expertise yet. I'm reading this textbook called Physics from Symmetry. Mm-hmm. I'll put the author. I forget the author, but there's this. It's an amazing textbook, Physics from Symmetry, and it's going through talking about how to build up physics from an axiomatic perspective of like, what if the symmetries are our axioms? How do we build up a universe
Based on those.
And that sort of way of thinking about stuff came from something called Yang-Mills theory. Okay, this is Yang. His tour de force, the reason why he's considered the great, right? Like this parody stuff is cute.
Yeah.
Okay.
Yeah.
The real reason why he's considered like one of the greatest of the 20th century is because of the Yang-Mills theory. So Yang's been obsessed with symmetry for the very longest time, right? And Weil started working on these. Hermann Weil started working on symmetries in physics. He piggybacked off of Noether and he renamed these symmetries something called gauge symmetries after like the gauges of railroad tracks and how they're all like, standardized.
I literally remember being in Terrace at Princeton and hearing any number of you guys talk. Someone was constantly on about gauge theory
because
constantly.
Dude, gauge theory, once I mean, I'm just getting into it with this textbook and it's like intoxicating how beautiful it is.
Okay.
Like imagine, it's completely inverting the logic of how you want to study the universe, right? Because it's saying like, it's postulating a symmetry to derive a force, right? It's saying we can take it as an axiom the fact that these symmetries exist, and then ask what is the kind of universe that we would live in if these symmetries exist, right? It's almost, dude, it's like, dare I say, a little religious in some sense. It's insane, right? So here's the only thing that I'm going to say about like sort of how the math that works. Well, we talked about how the wave function, right? It's a complex number.
Yes.
It's everywhere in space. If I change the phase of that wave function, that complex number, and the only thing I care about in terms of observables is the magnitude of that complex number, then it doesn't matter how much I change the phase.
Yes.
As long as I change the phase everywhere,
Yes.
the observable is going to be the same. That gives me conservation of charge. Okay.
Yes.
We can ask, what if I want to change the phase differently everywhere in space and time?
Yes.
Okay. So instead of a global symmetry, which is where I change the phase everywhere, I change the phase locally.
Yes.
Is there a local symmetry that I can do? And that's where what you can do is you can say, okay, if I change the local phase everywhere, then I can't really do a derivative in the right sense, right? Because the derivative, a spatial derivative in some sense, is the change between this quantity and this quantity divided by how far apart they are. Well, if I change this guy and I don't change this guy, now my derivative is really not well defined. If I change them by the same amount, then that change cancels out and my derivative is fine. But if it's a local thing, then the derivative is no longer well defined.
Yes.
But what I can do is I can compensate for it. And there was a famous physicist who actually said it's kind of like, if every city had its own local currency and they just decided to change their currency denomination or whatever, you would need some way, some exchange rate to make sure that I'm still paying for the right amount of stuff.
Yes.
Right? That's where a gauge field comes in. A gauge field is something you introduce to preserve the local symmetry where it's like, okay, I changed the phase here, but not here. What do I have to do to compensate for that, to make sure that all of my mathematics is still fine? I can still do a derivative. It's something that becomes like a covariant derivative where it depends on like where I'm taking the derivative. But all of these things introduce this thing called a gauge field, which is a new entity. It can also be known as a connection. And the sole purpose of this field is to connect the different symmetry choices that I have in all of these different neighboring points, and it provides a rule on how to compare all of my different thingies.
It's
right,
like a currency exchange is like the easiest analogy.
It's the easiest way to think about it,
and just in my head right now in this context.
Exactly, yeah. And it turns out that currency exchange is itself a field that is very, very much real, because that currency exchange has a certain value at each point, right?
Yes.
Depending on this city versus this city versus this city, that exchange rate has a different value at each point.
Yes.
So it becomes kind of like a field.
Yep, that makes sense.
Right? Kind of like, and so that field permeates space-time, and the real miracle of gauge theory is that field is, when it's curved, when it like changes, that exerts a force on the stuff that it's affecting. And that force it can manifest in real things. For example, in the electromagnetic field, that force is the electromagnetic force. That is the photon. The thing from the field, that gauge field, is like the electromagnetic 4 vector that becomes a photon.
Okay, now this is
getting crazy, but that's what Yang Mills was doing, dude.
Okay.
And Yang Mills was like, this is crazy.
Yeah.
What if I take this to new heights and I start applying it to the strong nuclear force,
right,
and the weak nuclear force?
Right.
This is he was actually at he had a shared office at Brookhaven at the time. Brookhaven had this thing called the Cosmotron, and he shared an office with Robert Mills, and the two of them start talking about Mills's like fascination with symmetry, right? And the two of them start thinking, okay, how can I make this something that has to do with nuclear forces, right? Can I make a quantum field theory for nuclear binding that explains all of the physics just based on symmetry? It's the start of something called Yang-Mills theory, right? It was not at when they devised it, it was not at its final form. There were still problems. They were getting these things called like massless particles, where like everything had no mass, and they're like, nah.
We have some photons.
But like not everything has no mass, and there were still a bunch of things that had to happen. Stephen Weinberg came in later to say, okay, we can actually combine that gauge theory with a kind of symmetry breaking, which we don't have to get into, but he introduced this idea of symmetry breaking. Then we get something like the Higgs, which comes in to give mass to the W and Z bosons. And so all of the standard model starts percolating out of this idea that we can take symmetries of stuff, right? And start creating physics from that axiomatic kind of framework.
We are definitely right? I have so many thoughts about this.
Are you starting to see why he's such a big deal in the 20th century?
No, I 100% get it. Because
right? It's not the parity experiment is nice, but this stuff is just like, whoa.
I feel the other time I felt the same way as this when we talk about the Heisenberg uncertainty principle. It makes me feel the same level of like,
yeah,
you know what I mean.
Makes you feel weird in a nice way, but in a weird way,
right?
Yeah.
Like it's from my layman's perspective, like that's the easiest like category analogy that I can, because I can much more almost intuitively understand like GR and like where Einstein was coming from. Like that's just for whatever reason easier for me to.
Yeah, he was a sage. That's what I mean. He was a sage.
That's what
not a magician.
Not a magician.
Yeah.
But this just feels like hand wavy, and it works. Like,
and
it works. But it's just like, can we go back to like, wait a minute?
Yeah. And I mean, I'm still honestly, I'll be honest, I'm still kind of there with you on that. Whoa. Right. I need to reread this textbook. I need to go through like some quantum field theory textbooks to really try to get what is going on. In my coursework, I went all the way up to quantum 3 in my graduate school. So we did like elementary quantum field theory. I know how to derive the Dirac equation and things like that. But Yang-Mills, I'm still sort of wrapping my head around.
You're the way you've created the journey.
But that's the way that I've talked about it now is sort of how I've constructed the understanding in my head.
Right.
You know?
And because I know you so well, it helps me. Like you've created a construction that I can engage in at a very, very rudimentary level. But you've at least given me the Lego blocks and the building blocks of the framework of like what it is and why it matters. And like why it's this inversion of the way to think about things by starting from this like some axiomatic symmetry argument as like your starting point to then build around versus like the other. It's just my brain. This is for those watching. This is what happens if we only do one story.
Because then I like really
then we just go in And so if you're still listening at this point in the pod, number one, leave a comment so we know that you actually like are on the journey with us.
Yeah.
Because part of this, like, I really am trying to grok these concepts and create at least a framework in my mind of what's happening here, such that as I decide what direction I want to take my academic interest for the rest of my life, I'm getting this nice potpourri buffet of everything.
Yeah.
And I can be like, QFT is a little interesting, but I think I'm going to stick with whatever. Anyway, C-gas-ting and go in that direction.
I mean, this stuff is just so deep. I'm like, as I'm like thinking about it, as I read, I have to read the sections over and over again to make sure I get every little thing, because it's just so beautiful. And I'm like, this can't be real.
Right.
I think about what we're just like the unitary 2x2 matrices that have a determinant of 1, like, are all of a sudden like what? So that's just the world is just you know, like
this is nerd paradise.
Yeah.
I know there are going to be some people who will be like, like who just can empathize and sympathize.
It doesn't make any sense to me, but at the same time, it's making so much sense that it's just like, what? Why does this work?
I don't.
It's weird, man. Yang Mill's theory is like really, really crazy.
I think we
like the fact that the standard model works this way,
right,
and all of the particles obey these laws that just come out of symmetry principles of just like, oh, I can do something to my thingy and it doesn't change. That means that there's a conservation of baryon number. That means there's a conservation of charge. That means there's a conservation of color. What?
The fractal community is gonna have a field day.
It's crazy, dude.
Everything is fractals.
Yeah.
Everything is symmetry.
Yeah, I mean, okay, so to close out on the story of Yang, he settled in the Institute for Advanced Study at Princeton for a while.
Yes.
That there's a photo of him with all of the classic.
Wait, it's so funny. When I was setting this up, I was like, oh, that looks like Princeton.
Yeah, it's the window, like the table.
Actually Princeton.
No, it is. It's the table and the window and the way the trees are. You just know it's Princeton.
I love how you also did not say anything.
No, because I wanted to be like, yeah, no, that was actually Princeton. That was at the Institute for Advanced Study. The architecture is all the same in that town. In that town, it's like there's a little bit of Gothicness.
Yes.
In like the Rocky College and like Blair, but then most of it is just like that classic American, like colonial architecture.
100%.
So he moved to the State University of New York. At Stony Brook, where he was the Albert Einstein professor. Then he actually became the first director of the Institute for Theoretical Physics there. Now it's called the Chen Ning Yang Institute at Stony Brook University. He was really big on scientific diplomacy. So in 1971, in the Nixon era, when China-U.S. tensions sort of thawed, he went back to China and he helped Chinese physics recover from that Cultural Revolution, which was really bad for academia and all of this other stuff.
Right.
He established a committee on educational exchange with China. He returned to Tsinghua University. And in his 1957 Nobel Prize speech, he actually described himself as a product of both Chinese and Western cultures in harmony and in conflict. I thought that was really interesting. So I looked really into this. There was an interview that was done by Stony Brook University that asked him, what did you mean by that? In harmony.
What do you mean by that?
Yeah, what do you mean by in harmony and in conflict? I'm a product of Chinese and Western traditions. He went into a lot of Chinese history. He started talking about how China had this amazing, 5,000, 6,000-year-old storied history. Kind of went into decline in the 19th century, and the British were trying to carve up China with the Opium Wars and all that other stuff. In 1900, there was the Boxer Rebellion.
Yep.
I don't know if you remember this. I remember this from AP World History. I had to learn about it. The Boxer Rebellion was a way for the Chinese to fight back on the imperialists. There was an alliance of 8 nations. It was the US, Russia, Germany, Japan, Italy, Britain, France, Austria, Hungary. So all of the guys who were fighting during World War II, all of these imperialist nations, they came together to subdue the Boxer Rebellion in 1900. They asked for reparations because that always works, and something like hundreds of millions of ounces of silver, which is an astronomical thing at the time, from China in reparations for the Boxer Rebellion. 10 years after that rebellion, the U.S. Congress passed a law saying that part of the U.S. spoils from all of that silver was going to go back to China to fund academia and scholarships. So they actually funded Tsinghua University in Beijing. They started Tsinghua University, which is where his dad was employed,
Right.
where he sort of got his start in academia. They also funded scholarships, which is the same scholarship program that he came to the US in. So it was this full circle sort of thing that Yang was involved with. He became very emotional, but that's what he meant when it's in harmony and in conflict. Right? Because in conflict, that's what started it. But in harmony, he comes to the United States. He goes to Chicago, earns his degree under Edward Teller, goes on to be one of the great physicists of the 20th century. After his retirement from Stony Brook, he goes back to China. He goes back to his alma mater, Tsinghua University, becomes the honorary director of the newly established Institute for Advanced Study over there. Mm-hmm. He really goes back and returns and pours a lot of effort into advancing fundamental disciplines and cultivating a new generation of scientific talent in China. And a lot of people give him a lot of credit for where China is in fundamental physics today.
I was going to say, this is what we talked about in a previous episode. In this, like in the US, we still have this probably outdated conception around scientific research in China as all being basically driven by this great power war between the US and China. And so there's an incentive to basically fudge the numbers in order to project this idea that they're making these advancements that are effectively hot air. Yeah. And that conception may have been true 20, 30 years ago, but it is certainly not true today. And you can not only see that in the fundamental research side, but you can also see that in how that research ends up in end user products, where the best phones, the best cars, like all the frontier modern Western things that we have historically been like, with the exception of really AI right now, which is still, we still have the edge. The Huawei stuff phones are better. The Yang Wang cars are better. Not only that's proven by them selling in the West, right? And feature for feature. And so this is like you can certainly say that some of these seminal figures have their roots that they've now reestablished are clearly bearing fruit. Yeah. And the evidence of that is undeniable at this point.
Exactly. Yeah.
It's, oh my God.
Yeah, exactly. And, he was an instrumental part of that reawakening of China's fundamental science and fundamental physics ecosystem. In 2015, he actually renounced his U.S. citizenship so he could obtain and resume his Chinese citizenship. He spoke candidly pretty much about this journey. He actually said that when he became a U.S. citizen, his father never forgave him for that until he lived, which that's crazy. That's crazy. I can understand, my dad would never do that, but if your dad does that and you want to, I can understand. So he went back to his Chinese citizenship. He loved the United States. He called it a beautiful country that had given him incredible opportunities to pursue science. He's also not one of these evangelists, these particle physics evangelists. When China wanted to make the next particle accelerator, he was actually against it because he was like, particle physics is not like going places. Yeah. What are you going to do with a larger accelerator? Yeah. You're not going to find new particles. Yeah. You're just going to make a bigger accelerator. Yeah. And everyone in the particle physics community was like, didn't talk to him for like 2 years or something. But, he was very candid about what he thought about where physics is going. It's an incredible life that he lived, Yeah. Coming up during the war, during World War II in China, which is not the best place to be in World War II. It's one of the worst, in fact, given all of the atrocities that happened under Japanese imperialism there. he managed to make it out, managed to create a name for himself in America, managed to not only create a name, but like, he's sitting down with Einstein and Feynman and the big guys, and he's holding his own. And to those in the high energy physics community and the particle physics community and the mathematical physics community, Yang is one of the Mount Rushmores.
Yeah.
Yang-Mills theory is really, really like fundamental. And I hope you get an idea of, now that I've talked to you about like what it really means, like how it turns its head, how it turns the head of all of physics to become this axiomatic kind of pursuit from symmetry to laws rather than from laws to the other way around.
Everything else.
Yeah. He died very recently, and we have one final photo of Chinese students lined up at Tsinghua University to pay tribute with photos, with flowers. There was a line to pay respects to him. He was a huge deal in China, as he should be.
As he should be.
He was the first Chinese to win the Nobel Prize, along with Tsung-Dao Lee. So, together. But yeah, he's completely transformed physics in the 20th century, right? One could say there's few people that you could say is the father of the Standard Model, but he'd be one of them. Yeah.
It's just what a journey.
Yeah.
One big story.
Yeah.
To one of the goats of the 20th century, Nobel Prize winner.
I know it was long, but I really had to. I mean, I had to share with you all of the things that I found. I mean, I knew about Yang-Mills theory, but not to the extent.
Yeah. It's just an incredible life story. It has everything.
Yeah.
It has war, love, geopolitics, fundamental research, those who should have been there with you, those who were not able to be there with you. This sort of intersectionality, like, globalists, like everyone's like, oh, the globalists are terrible. I mean, we have now been given this gift because, again, we have allowed smart folks to come in and go to institutions like Chicago, go to institutions like Princeton, go to Stony Brook, and give back something that is just, I'm going to be thinking about this one for some time. This was our one big story on one of the goats of physics, Chen Ning, both on this parity concept, conservation of parity, and Yang-Mills theory, Nobel Prize winner. We're going to claim he's a Princetonian.
Yeah, it counts.
He was there.
It counts.
There's a picture of him there. I sat where he was sitting.
Yeah.
So we'll take the win. But in all
probably
seriousness,
drank a few beers there on that table too.
100%. To what a wonderful life lived, and this is meant to be a love letter to the work, and maybe unlocking interest for some listeners who might not have been interested in this area, that one day may continue on the legacy and build on the foundation that's been here, or that's been built rather. As always, my name is Lester Nare, joined by my co-host and our resident PhD, Krishna Choudhary. Thank you for joining us for this deep dive special episode. We will be back next week. This is From First Principles.